Hello, we are Group 6 and we will be discussing Experiment 6, the determination of copper and zinc in water sample using flame atomic absorption spectrometry. Atomic absorption spectrometry, or AAS, is a tool for measuring quantities of chemical elements present in samples by measuring the absorbed radiation by the chemical element of interest. This is accomplished by taking advantage of the differences in the energy of each element. One AAS technique involves flame atomic absorption spectrometry, or FAAS, which utilizes flame to atomize the sample or convert the samples into their gaseous atom components. FAAS, or direct aspiration determinations, are normally completed as single-element analysis and are relatively free of interference. So when a sample is injected into a flame where the ions are reduced to elements and are vaporized, the elements present in the sample absorb light at specific wavelengths within the UV-vis spectrum. A light beam with a single specific wavelength for the element being measured is directed through the flame to be detected by a monochromator. Then, the light absorbed by the flame containing the sample is compared with the absorption from known standards to quantify the elemental concentrations. Additionally, FAAS is a sensitive and a selective technique with highly efficient analytical capacity, making FAAS useful for the analysis of metals, especially in environmental applications, due to the need for lower detection limits and for trace analysis in a wide range of samples. With this experiment aims to get acquainted with the principles and operations of FAAS, as well as to employ FAAS in quantifying the concentrations of copper and zinc in various water samples.
The reagents and the materials used in the experiment are presented in this slide. The procedure followed in the experiment was divided into three parts, which are the preparation of standard solution, the preparation of the sample, and the actual absorbance measurements and statistical analysis. For the standard solutions, 10,000 ppm copper stock solution was firstly prepared from copper 2 sulfate before securing 6 clean volumetric flasks and arranging 0, 1, 2, 3, 4, and 5 ppm standards. Similarly, the zinc standard solutions were initially prepared from zinc nitrate before producing 6 standards. For the sample preparation, 10 ml of 0.5 molar nitric acid was diluted to 100 ml by the sample waters, which are the DPSM top water and the deep well water. For the last part, absorbance measurements were obtained using the AA6300 atomic absorption spectrophotometer. The absorbances of the standard solutions were first determined before the samples were subjected to the spectrophotometer. Afterwards, the data collected were used to compute the concentrations of copper and zinc in the samples.
Now, for the results. Shown in the slide are the raw data for the standard solutions for zinc and copper. From the raw data, the group plotted the average absorbance of the standard solutions to its respective concentrations. The equations were then used to calculate the zinc and copper concentrations of DPSM water and deep well water. The equation of the calibration curve of the zinc standard solution is y is equals to 0.09321x minus 0.0149 with an r squared value of 0.9582. Using the equation, the obtained concentrations are 0.40173 ppm for DPSM water and 0.49947 ppm for deep well water. The table shows the average absorbance and the zinc concentrations of the two samples. The equation of the calibration curve of the copper standard solutions is y is equals to 0.1003x plus 0.0875 with an r squared value of 0.9068. Using the equation, the obtained concentration is 2.0659 ppm for DPSM water and 2.1002 ppm for deep well water. The table summarizes the average absorbances and copper concentrations of the two samples. Now, upon comparing the values, both zinc and copper concentrations of deep well water are higher than DPSM water. Additionally, there is more copper compared to the zinc content of both samples. The concentrations were calculated by adding the y-intercept to the absorbance value of the unknown concentration and divided it by the slope, and is then multiplied with the dilution factor, which is 100/90, as seen here in the slide.
Zinc is a metal commonly found in the Earth's crust as well as food, making it less hazardous than copper. Hence, deteriorations in the neuronal and physical growth are attributed to the lack of zinc intake. Albeit this, exposure to high zinc concentrations damages the body. This metal enters the water system through artificial pathways, such as the byproducts of steel production or coal-fired power stations, or from the burning of waste materials. Aside from this, zinc also enters the water system because of the zinc-coated pipes utilized to prevent rusting, as well as zinc from fertilizers that may leach into the groundwater. This can be attributed as to why there are traces of zinc found in both the deep well and DPSM tap water samples. In drinking water, the presence of zinc at concentrations higher than 5 ppm leads to a metallic taste. Thus, drinking water should not contain more than 5 ppm of zinc. Meanwhile, copper is a naturally occurring metal found in various places such as bodies of water and soil. Aside from this, copper is considered an essential element for living things like human. However, like zinc, toxicity or complications occur at high levels of copper. When this element enters the water system, it is carried in the surface waters as a free ion or compound bound to particles suspended in water. Despite this, studies show that the water-soluble copper compounds also enter the groundwater. This might explain why the data shows that copper concentration is relatively high in deep well water. Accordingly, the average copper concentration in tap water ranges from 20 to 75 ppb, even reaching 1 ppm. The data from the experiment reveals that the copper concentration from the DPSM tap water is higher than 1 ppm. This high concentration can be attributed to the dissolved copper in copper pipes and brass faucets when the water is stuck in the pipes overnight. In drinking water, copper concentration should not exceed 1.3 ppm. Therefore, it is recommended to perform water treatment to reduce corrosion significantly if more than 10% of the samples exceed 1 ppm of copper.
To further discuss the results, it could also be observed that deviations of the experimental results from the known concentrations of zinc and copper in the water samples were present and evident. The determination of the zinc concentration in the DPSM water and the deep well water samples have exhibited 71.447% and 74.446% errors respectively. Similarly, the obtained results for the copper determination for the aforementioned samples have obtained 11.046% and 11.047% errors. Primarily, these errors could have arisen from the deviations of the sample from linearity, which could be attributed to the presence of high elemental concentrations of zinc and copper, as well as other atomic species. This occurrence is due to the unwanted interactions between the atoms of the analytes with each other or with other present species, which could affect the relationship of the sample absorption with its actual analyte concentration. Moreover, deviations from the linear relationship could also occur when over-discharge occurs in the instrumental HCl, wherein the gases of the lamp contaminates the sample, thus affecting the detected absorption of the analyte. These possible sources of error could be prevented through proper sample preparations and appropriate instrumentation.
For the conclusion, FAAS was used to measure the zinc and copper concentrations from various water samples. FAAS measures the absorption due to atom excitation. FAAS utilizes atomization or the conversion of samples into a gaseous form. The values obtained from the calibration curve were then compared to the concentration of the samples for error analysis. The following values were obtained and the percent errors, shown in closed parentheses, were calculated. The deviation as seen from the percent error can be attributed to the interaction of the analytes with the contaminants and contamination from the gases of the lamps. Following these conclusions, the researchers would like to recommend adding other spectro and electroanalytical techniques to confirm and determine the accuracy of FAAS. Preparatory steps for removing contaminating agents is also strongly recommended as to minimize the interferences during analysis.